Okay, so we've already talked about Charles's law, which relates temperature and volume. We've done Boyle's law, which is pressure and volume. And now we're going to talk about Gay-Lussac's law. And I'm going to go through it pretty quickly for a reason. Gay-Lussac's law relates pressure and temperature. Okay, because remember, there's all these variables that are involved with gases. How much you have, the pressure, the temperature, and the volume. And so they're all directly related to each other in some way, shape, or form. So pressure is a direct result of collisions between gas particles in the walls of their container. Remember, they're bouncing off the walls. If you increase the temperature, it's going to increase the number of times they hit the wall and the energy with which they hit the wall. So raising the temperature should also raise the pressure if you don't let the volume change. So if I had, let's say I had a hairspray can, okay, and it's got all this little gas particles inside there, and it's a closed container. In other words, the volume of it can't change. Well, if I start heating that sucker up, okay, those little gas particles start bouncing off the walls harder and harder and harder and harder. And eventually, if they get hot enough and have enough kinetic energy, they have probably got enough kinetic energy to burst the can. That's why if you look on hairspray bottles and hairspray cans, it says do not heat above what you don't set it on a radiator or whatever. Don't heat them because this could definitely happen. Okay, so that's the idea. Gay-Lussac's law states that the pressure of a fixed volume of gas varies directly with the Kelvin temperature. So again, as temperature goes up, pressure goes up. This is what it looks like. So P1 over T1 equals P2 over T2. And again, it has to be an absolute temperature. And I'm going to just do a quick example. So pressure of oxygen gas inside a canister is 5 atmospheres at 25 degrees. Canisters at a camp high on Mount Everest, and the temperature falls to -10. What's the new pressure? So P1, T1, P2, and T2. So the pressure is 5 atmospheres. The temperature is 25, but again, I'm going to automatically add 273 and get 298 Kelvin. They want to know what the new pressure is, so that will be in atmospheres because our units match. And -10 again plus 273 equals 263. So again, set it into your equation. 5 over 298 equals x over 263. I'm going to do my cross multiplying here. I get 298x equals 1,315. I'm going to divide by 298. And you get 4.41. Okay, which makes sense because the temperature went down, we would expect the pressure to go down. Okay, so there is another example of a different gas law. There's a fourth one called Avogadro's law. And this one doesn't deal necessarily with temperature and pressure, but it deals with volume and the number of moles of a gas. And again, if you think about it, if I have a container and it's got 5 particles, 6 particles floating around inside it, it's going to have a certain amount of pressure. But if I double the amount of particles in there, it's going to double the pressure or double the volume, one of the two. So Avogadro's law says volume is proportional to moles, where N1 is the moles of the gas. So we're getting back into the moles thing. Don't panic, it'll be okay. N2 is also the moles of the gas. So this, in the first situation when I was describing up here, I had 5 moles. Now I might have 12 moles. As this increases, so will the volume, as long as pressure and temperature are constant. Okay, so I'm not going to do a problem with that one because what I'm going to do is I'm going to combine them into something called the combined gas law, which involves pressure, volume, temperature, and moles all in one equation, and you can use this equation to solve any kind of a situation where you are changing the values of the pressure, the temperature, the moles, or whatever it is. So combined gas law states that the relationship among pressure, temperature, and volume of a fixed amount of gas, pressure and volume are inverse. Pressure is directly proportional to temperature. Volume is also directly proportional to temperature, and it's also proportional to the number of moles. So what it looks like is it looks like that, or if you throw in the moles part of it, it looks like that. And this is probably the easiest one to go with, just because it's P1, V1 over T1, N1 equals P2, V2 over T2, N2. Okay? The P's and the V's are on the top, and the T's and the N's are on the bottom. And so N is the number of moles of gas, that are in the container, and you're going to use this anytime you change the conditions. You change the temperature, you change the pressure, that kind of a thing. And you can use this one instead of trying to remember Boyle's law and Charles' law and Gay-Lussac's law and Avogadro's law. You can just use this one, and this is the one to know. Okay, so if I have a problem, what I want to do is, first of all, I want to identify what variables are present. Do I have pressure, volume, temperature, or moles? Whatever I don't have, oh, here's the units that go along with them. Pressure is going to have certain units: ATM, kPa, millimeters of mercury, torr, psi. Volume are going to be units in liters, so milliliters, deciliters, hectoliters, or meters cubed, decimeters cubed, centimeters cubed. Temperature is going to be either degrees Celsius or Kelvin. And N is going to be in units of moles, but you might have to convert grams, so you want to watch out for grams too. Okay? So, look at your variables, identify what you have in the problem. Match the variables with the initials or the finals, situations, ones or twos, and then anything that is not mentioned or anything that remains constant in the problem, just drop it out of that gas law. Okay? And I'll show you what I mean by that. Make sure the units for the different variables match. In other words, both your pressures are in atmospheres, both your volumes are in decimeter cubed. Whatever it is, make sure that those particular units match. Convert beforehand, and then just plug it into the combined gas law. So let's look at this one. So if I'm looking at this gas law, and I see this, I'm going to recognize that as a volume, I'm going to recognize that as a temperature, and I'm going to recognize that as a pressure. It is then allowed to expand to a new volume at a temperature of 45 degrees, and they want to know what is the new pressure. So first thing I'm going to notice, P1, V1, T1 are all mentioned, but there's no mention of moles. And if there's no mention of moles, we're not going to use it at all. So the pressure is 541 millimeters of mercury. Volume is 3.96 liters. Temperature is 87. And again, immediately, do yourself a favor and just automatically, if it's not in kelvins, add that 273 on before you forget. Under P2, V2, and T2, the new pressure is what we're looking for. The new volume is 8.34 liters, and the new temperature is 45, and again, add 273, and you get 318 Kelvin. So when I'm solving this, I notice that there is no mention of moles or grams. All I have is pressure, volume, and temperature. The other thing I want to notice is that my units match, which means I'm going to be solving for pressure in millimeters of mercury, which is fine. They don't specify. So my gas law looks like this. But because it doesn't show anything about moles in the problem, you know what? I'm just making that go away. I'm just going to erase it and not even count it. So what I'm going to count is I'm only going to deal with the P1, V1s, and T1s. So, and the P2, V2, and T2. So I'm going to plug these numbers in. 541 times 3.96 over 360 equals X times 8.34 over 318. And again, I'm going to cross multiply, and I absolutely recommend highly that you do this. So I'd have 541 multiplied by 3.96 multiplied by 318. So I'd get a huge number, 681,270 equals, and I'm going to multiply these three together. 8.34 times 360 times X, and I get 3002. So to solve for X, I'm going to divide. Everything here is multiplied or divided. There is no adding and subtracting except with these temperatures. That's it. So X ends up being 227. Now the thing is, with this combined gas law, it's not as obvious to see how the relationship works out. So I'm looking at this, I'm thinking the volume went up and the temperature went down, so maybe it makes sense for the pressure to go down. Yeah, sure, the volume's much bigger. They're not going to be able to collide as often with the walls. They're moving slower. Sure, makes sense, but sometimes it's not so easy to tell. All right, so go ahead, pause the movie, see if you can solve this one, and again, pay attention to what your units are. This is a pressure, this is a temperature, and this is a volume. They want the new temperature at a new pressure and a new volume. Okay, so set up your variables. Pay attention to your units and solve it. Okay, so my pressure is 80.5 kPas. My volume is 451 milliliters. And my temperature is 165 plus 273. It's 438. Okay, my new pressure is 1.11 atmospheres. Okay, so immediately I'm recognizing possible problem there. Volume 0.155 liters. Again, possible situation. Temperature is what we're looking for. We're looking for it in Celsius, but remember, when you're doing a gas law, doesn't matter what it says here. If you're using the gas law, it has to be in kelvins. Okay, so my Kelvin temperatures match. Not so much with my volume units. So what I'm going to do is I'm going to change from liters into milliliters. If you remember, the conversion is 1e negative 3. So 155 milliliters. So that's good. I got that one done. Now I need to change my pressures, and it doesn't matter which one you choose, because everything that's happening here other than temperature is multiplication or division. And that's all, whatever the term is, associative, commutative, something like that. So I'm going to change the kPas. 1 atmosphere, 101.3 kPas. And you get 0.79 atmospheres. Now my units all match. So now I can go do that combined gas law. And again, I notice there are no moles or no grams. So all I'm going to do is P1 V1 over T1. I'm dropping the N1, P2 V2 over T2. And I'm dropping the N because there is no N in my problem. Why make my life difficult? So all I'm going to do is plug in the numbers. 0.79 times 451 over 438 equals 1.11, 155, not 0.155, and x. And again, just cross multiply. So 438 times 1.11 times 155 is 7535, let's call it 8, equals these two multiplied times x. 356x. And again, everything is multiplied and divided. So I'm going to divide here. I'm not going to subtract. And I get 212. Okay, and again, remember what I was looking for, Kelvin's temperature. All right, in order to figure out the temperature in Celsius, anytime I'm doing this gas law, it has to be in kelvins. But once I've done the gas law, all I have to do is subtract 273, and I can find the temperature in Celsius, negative 61 degrees C. And yes, it is possible to have negative Celsius temperatures, not negative Kelvin. Kelvin stops at 0, but negative degrees Celsius is possible. Okay, now let's go ahead and take a look at this one. 17.5 grams, that's a new one, of chlorine gas, has a volume, so there's my volume, temperature, pressure. What volume would this grams occupy at 100 degrees and that pressure? So this is going to be a long problem because it's got everything, P1, V1, T1, and N1, okay? And I'll talk about the N1s in a minute, so let's put in the values here. Volume is 96.3. Pressure is 1.25 atmospheres. Notice I'm writing the units. Temperature is 25 plus 273 is 298 Kelvin. Okay, I'll get to that grams in a minute. And then they want to know a new situation. What volume? So that would be X. 100 degrees C is 373 Kelvin. 1,000 millimeters of mercury. Okay, and again, they need to match units, so I'm going to change millimeters of mercury into atmospheres. And that's quite frequent. Very often you will see calculations done in millimeters of mercury. So 1.32 atmospheres. Okay, so now let's talk about these grams thing. Okay, grams is not the same thing as moles, but it is related. And so what you need to do before you do the problem, just like how we were changing temperature into kelvins, you really need to change from grams into moles. So 71 grams, because it's Cl2, is 0.246, and that would be your moles. Same thing with the 82.6 grams. Do the same thing, 1 mole, 71 grams, 1.16 moles. So now all my units match. I have filled in all the variables. I have changed grams to moles, so all I'm going to do is put it into the entire equation, P1V1 over T1N1 equals P2V2 over T2N2. So 1.25 times 96.3 over 298 times 0.246 equals the entire other side, 1.32 x over 373 times 1.16. And again, I'm going to cross multiply. So I'm going to have 4 numbers multiplied over here, those 4. 1.25 times 96.3 times 373 times 1.16. A lot of math. 52,080, call it 84, equals, now I've got number times variable. So 298 times 0.246 times 1.32 times x gives me 96.8x, divide. And you get an answer of 538, okay? And in this case must be liters. Let's make sure I did that right. 298, 246, 1.32. Looks like I did it right, okay? Seems a little bit high, but maybe that's because I got a lot of stuff in there. I don't know, okay? So that's the idea. Pay attention to your units. Pay attention to what things match up where, and it helps to be able to just write it on top of there if that makes it easier for you. But then just be careful with your algebra because they can get complicated.